Welcome to LC Insider, your weekly insight into the world of printed electronics, flexible interfaces, and smart design, powered by LC Electronic, the world of printed electronics in one place. Designing with printed electronics. This episode is a practical guide for engineers and product designers who want to use printed electronics in their projects. When we say printed electronics, or PE, we mean using conductive inks instead of etching classic copper paths. It's a new way to design circuits that are flexible, light, and creatively integrated into your product. In the next minutes, we'll walk through the full process, from choosing materials to testing a working prototype. Think of it as a tour from concept to first functional sample. Let's begin with the substrate, the base of your project. The right base material is critical. It affects mechanical strength, flexibility, temperature resistance, and how well the inks will actually stick. If you are designing wearables, touch panels, or textile sensors, you will typically choose from a few key substrates. PET, for example, Mylar A, is a popular choice. It is relatively cheap, well understood, and can handle temperatures up to around 130 degrees Celsius. If you need more strength and higher thermal stability, you can move to PEN, for example TNX Q51. It offers better performance and can usually handle temperatures up to about 180 degrees. For applications that need stretch, such as wearables or textile-based sensors, PU-coated textiles are often used. They allow some mechanical deformation while still giving a usable surface for printing. At LC Electronic, we help choose the right substrate already at the briefing stage. The goal is simple: to avoid classic problems like cracking, shrinking, or poor ink adhesion later in the project, when changes are more expensive. Once the base is chosen, it's time to talk about inks. This is where conductivity begins. Inks must match both the surface and the function of the layer. The key properties you care about are resistance, durability, and flexibility. Silver inks, for example, Henkel Loctite ECI 725A, are very common because they offer high conductivity. They are a good choice for signal lines, bus bars, and other paths where low resistance really matters. Carbon or hybrid inks are more affordable and are often used for low-power touch layers, button contacts, or shielding where extreme conductivity is not necessary. Then there are materials like PEDOT::PSS, for example Heraeus Clevius. These inks are transparent and flexible. They are great when you need see-through electrodes, for instance in touch sensors or special optical layers. You will also need dielectric inks, such as Elantis PD4070. These are used as insulation layers to separate conductive traces or to protect sensitive areas. In practice, we always recommend testing inks with the real substrate materials. Laboratory data is useful, but nothing replaces printing a few samples and checking how they behave in your specific stack. Now let's move to layer design, which is where printed electronics really becomes different from classic PCB work. In printed electronics, you don't just draw tracks on one or two copper layers, you design functional layers like a three-dimensional system. It is closer to thinking in 3D CAD or even in advanced graphic design than to a simple board layout. Each layer has its own job. One layer may be responsible for conductivity, another for insulation, another for optical effects, or for protection against humidity and wear. A typical printed electronics design may include anywhere from 3 to 9 layers, each with different properties such as thickness and resistance. For more complex shapes and touch-based systems, LC Electronic uses a mix of CAD tools and graphic tools to capture both the electrical and the visual intent. There are also some important design parameters to keep in mind. Typical line widths are in the range of 150 to 250 micrometers. Layer thickness after screen printing is often between 4 and 20 micrometers, while inkjet printed layers can be as thin as 1 to 3 micrometers. For silver traces, a common target is a sheet resistance of less than 0.05 ohms per square, at a thickness of about 25 micrometers. These numbers help you estimate whether your design will meet the electrical performance you need. Once the design and materials are selected, we move into prototyping and testing. At this stage, we print test samples. The printing method, whether screen printing or inkjet, and the curing process, whether in an oven with infrared or with UV, all depend on the type of ink you are using. The basic sequence is simple. First, the ink is printed onto the substrate. Then it is cured using heat or ultraviolet light, according to the manufacturer's specification. After curing, we check basic parameters: resistance, continuity, and surface quality. If the electrical and visual results are promising, we move on to stress tests. These tests can include bending cycles, humidity exposure, and thermal cycling. The idea is to see how the printed layers behave in conditions that are closer to real life. We follow standards such as IPC 9204 and ISO 9227, and we can prepare documentation that supports CE or FDA approval processes if needed. This is important when your printed electronics become part of medical or safety critical devices. There is one more important step: integration with classic electronics. Printed electronics almost never live in isolation. In the end, your printed sensor, antenna, or touch layer must be connected to classic PCBs, connectors, or modules. That means you have to plan the interface from the beginning. You will need to decide on solder pad layouts, connection types, and how you will guarantee signal continuity over time. Common methods include ZIF connectors, where a flat printed tail is inserted into a zero insertion force connector, silver conductive glues, which bond printed traces to pads, and low temperature solder, for example a SUN 42, BI 57, AG 1 alloy, which melts at around 138 degrees Celsius. At LC Electronic, we help create these hybrid designs, combining flexible printed layers with rigid boards. We support the choice of compatible materials and test the functional connections under load. So, what is the big picture for designers? Printed electronics give you much more control over form, material, and function. Instead of treating the circuit as a rigid piece hidden inside the device, you can turn it into an active layer that shapes the user experience. You can start with something simple, like a thin pressure sensor, and then add more layers on top. For example, a protective cover layer, a printed backlight, or even an NFC antenna. Each new layer adds a new feature. At LC Electronic, we work with engineers to choose the right materials, tune the inks, and simulate and test as early as possible. The result is that you gain full control over the look, the function, and the cost before you ever commit to large-scale production. If you want to dig deeper, there are many useful resources. Henkel, Heraeus Klevios, Sun Chemical, and Elantas all provide detailed information on their printed electronics materials. And if you need help with ink selection, layer design, or prototypes, you can always contact LC Electronic. We don't just print, we guide you through the whole journey from idea to working, testable hardware. Welcome to LC Insider, your weekly insight into the world of printed electronics, flexible interfaces, and smart design, powered by LC Electronic, the world of printed electronics in one place. Stay curious and stay connected. Subscribe to LC Insider for your weekly dose of HMI innovation, or follow LC Electronic on LinkedIn.